Okay. Welcome everybody. If you are just joining, we apologize. We've had a lot of wind here on the east coast of the United States, and we've been losing power. I've had the power flicker on and off today, so just bear with us. I believe that we can go ahead and get started in just a few moments. So thank you for joining us, and we'll be ready to go in just a minute. Okay. Bo, did my screen pop up okay?
Yeah, so David, is anybody in the meeting now?
What's that?
Is anybody in the meeting? I see a lot of people are still in the lobby.
Yes, I am okay. I'm going to admit all. Okay.
All right, cool. Yeah,
Okay.
they're in.
All right, everyone. Good morning, good afternoon, good evening. Uh, my apologies. I think many of you know that we've had some weather events here on the east coast of the United States, and we have a lot of wind, and my power has been flickering all morning, as well as Becky Dipple has lost her power. So apologies for a little delay, a slight delay, but hopefully everyone is joining now. We'll give folks just another minute or so to join. And Bo, can you see my screen?
Yeah,
Okay,
that's good.
excellent. All right, so between you and me, we'll try and figure out how to get this going. I
Sure.
mean, I just actually reminded myself we've actually been putting on these webinars at IWCS for now 10 years. And you'd think one of these months I'll figure out how to do this stuff. But anyway, so we welcome everyone again. Thank you for joining us. Good morning, good afternoon, good evening. Um, we'll go ahead and get started. And again, as I see folks in the lobby, I'll try and make sure they get let in. But anyway, my name is Dave Cadu. I am honored to be the CEO and director of IWCS, and I'll be hosting today's webinar. Just a few housekeeping items for those of you who haven't joined us in the past. You are part of a larger audience. So with that, all participants will remain in listen-only mode. And also, as a reminder, this webinar, like all of our others, is being recorded so that you'll be able to either watch it again or share it with your colleagues from our IWCS website. And you can find on our website all of the webinars from the past 10 years, which is great. I mean, it's awesome that we can have such great papers like today's paper that was delivered in Pittsburgh to be archived on our website. So hopefully that's useful to you and all of our participants. We encourage you to enter any written questions at any time during the presentation using the chat panel. And that should be on the right of your screen when you click on the chat. After typing in your questions, be sure to hit the send button and we will address your questions time permitting at the end of the presentation. So again, today's event is being hosted by our IWCS Cable and Connectivity Industry Forum, and we do offer a series of webinars on important trends and technologies from the perspectives of our supply chain partners and sponsors each month. So today, we're honored and welcome Bo Zhu. He is the R&D Materials Manager for Superior Essex Communications and resides in Georgia, USA. Bo will be presenting his paper today on the effects of temperature rise on data transmission performance in power over Ethernet PoE cables. Bo is a materials engineer at Superior Essex Communications. He earned his doctorate degree in polymer engineering from the Georgia Institute of Technology in 2010, and his master's in materials science at the Zhejiang University back in 2004. Bo has an extensive background in polymers, and with over 30 scientific and conference papers he has published, and he also holds over 10 patents. Prior to Superior Essex, in 2017, he worked as a packaging analytical scientist at the Coca-Cola Company. So we welcome Bo. Thanks for being with us and presenting this excellent paper that you delivered in the 2025 IWCS. Take it away.
All right. The screen's on. Everybody can see it. David?
Yep. Looks good.
Good. Thank you, David, for the kind intro, and thank you everyone for joining today. Really excited about this opportunity to share our 2025 IWCS work. And as David mentioned, I'm Bo Xu, a materials engineer at Superior Essex. And thanks to my colleague, Dr. Germer, and as a co-author, his contributions were essential to this study. Today, I will talk about thermal aging and the bit error rate performance in power over Ethernet cables. We will examine how high temperature and long-term aging affect signal integrity and reliability. This matters because the PoE cables can both power and high-speed data simultaneously, making them more vulnerable to heat. More power means more heat, and more heat sparks more problem. Our goal here is to better understand electrical change and heat and how they translate to bit error rate performance over time. By the end, you will know what changes from heat, why, and how to design a better, a tougher PoE cables. So with that, let's get started. Over the last 20 years, the PoE technology has come a long way, from a simple 15 watt to 2-pal to today's 100-watt 4-pal, powered by PSE, or the power source equipment. The PDs, or the powered devices, start many with IP phones back in the day, pretty basic, and then expand to security camera, sensors, radio phones, LED lighting, digital displays, and even TVs and computers. Looking ahead, the future PoE systems will push toward 200 watts. But here's the problem. The higher power means higher current. And the higher current generates more heat in the cable. So now we have two key questions. How much the heat builds up? And what does that heat do to the cable? To address in the first question, the heat generated in the cables during operation can rise significantly, especially when tight bundled. Our early work from Thibault Landau study in 2017 showed the big bundles can get really hard inside. Some studies have even shown the center of the bundle can reach nearly 200 degrees Celsius under extreme conditions. At those levels, the cable materials, especially insulation and jackets, began to thermally age, soften, and even fall apart. The materials degradation shapes the electrical performance. ultimately impacting long-term reliability. So let's look at what temperature actually does to the cable materials. This slide shows two examples. On your left is polyolefin insulation. After just 10 days at 120 degrees Celsius, it became very brittle. And you can see it in the photo clearly, it's falling apart. On the right is PVC-jacketed. Same thing, after 10 days at 136 degrees, the PVC showed clear material loss, shrink, hardening, and even failed the T&E tests. In contrast, the fluoropolymers really stands out here. The FEP stands up to 232 degrees Celsius and PVDF up to 150, while still keeping their electrical and mechanical properties solid. The flexible PVC jackets, by comparison, are typically rated only to 105 degrees Celsius and start aging much earlier. So the material choice matters a lot. Now, let's look at why the cable materials degrade. Here using the jacket as example. When the jacket gets heat, several processes happen simultaneously. External tags like oxygen, moisture, chemical migration and release, and the interaction with other cable layers. For example, plasticizers can migrate out of flex PVC, making the jacket stiffer and more brittle. The polymer itself can release some volatiles, including small amounts of hydrogen chloride, which speed up aging. Together, all these effects weaken the cable materials, making them less flexible and reducing long-term reliability. And in the high power PoE, this all gonna happen even faster. So far, we see how the heat changed the cable materials like weight loss, polymer degradation, and mechanical change in jacket. But that raises another important question. If the material chemistry changes, does the file behavior change too? The answer is yes. But how? To find out, in 2023, we ran the burn tests in the UL standard tunnel, comparing the thermal aged cable versus unaged ones to see how aging affects the flame spray and smoke generation in prime-rated PoE cables. So what did we find? The both aged and unaged cables actually pass the platinum burn. In some cases, the aged cable even show a shorter frame span and less smoke. The full details are in our 2023 IWCS paper if you want to dig deeper. But the key point is this: the thermal aging changes the file behavior. So it's really to be evaluated through testing. Now, let's move on. How do we know the cable materials have degraded too far? To answer that, we use critical weight loss, CWL, based upon the UL 444 mechanical criteria. Post-aging, the PVC jacket must hold elongation about 50% and tensile strength about 85%, or it's failure. In our 2022 study, we found that the critical weight loss varies from 2 to 5% across those 5 PVC jackets. And different PVCs are felt differently. Some are sensitive to the weight loss, but others are not. Using this critical weight loss and thermogrammetric analysis, or TGA, we predict lifetimes. Based on our model, Only 1 in 5 PVC jackets can last over 20 years at 6 degrees Celsius. But at 75 degrees Celsius, none make 20 years. When the temperature hits 100 degrees Celsius or above, the lifetime crashes from years to just days. For example, all these PVC jackets survives 10 plus days at 100 degrees Celsius, confirming the wall can be rated for 75 degrees Celsius. However, none of them survived 7 days at 136 degree, so not qualified for 105 degree rating. And these results on high temperature side aligned well with our aging TNE test, supporting our predictions on the low temperature side. Overall, these results show you the thermal limits of PVC jackets. After looking at the materials degradation, let's see how this impacts the electrical performance. In our 2022 study, we examined cables aged at 100 degrees Celsius. On the left, you can see the lax cover near the crosstalk gradually shifting downward with aging. That means more crosstalk and less margin. On the right, we track the lax margin. Big job in the first 30 days, and then left off. After about 46 days, the cable finally felt the lax limit. So even at a moderate temperature, like 100 degrees Celsius, the electrical performance degrades. It just takes time. In our 2023 study, we pushed even harder. The cables were aged at 136 degrees Celsius, but tested at room temperature. What we found is that the weight loss strongly correlates with crosstalk changes. As the PVC loss material, it shrinks, comprising the cable core, squeezing pairs together, and then cross goes up. Meanwhile, the PVDF jacketed cable had almost no weight loss. The performance stayed steady. And simply put, the unstable jacket caused electrical failure, while the stable materials preserve performance. Okay, so when we push cables to their limits, like high temperature, high frequency, they act out. And honestly, who can blame them? Even when engineer can get a little bit crispy and those harsh conditions, like hot and noisy, who likes it? Look at those insertion loss curve from room temperature to 136 degree. The people is basically having a really bad day. These combined stresses change a lot, including insertion loss, crosstalk, ACR, impedance, and more. And all these changes show up in one place, the bit error rate, the metric that matters to users. That's exactly what we measured. So let me show you how. Here are our setup and test method. We tested 100-meter cables in an environment chamber using both thermocycling and isothermal aging at elevated temperatures, and then cooled them to room temperature. After each stage, we measured the electrical parameters and bit error rate using spin rate, N4U, BR tester, and Fluke DSX 5000. Why couldn't done? It simulates real-world applications, since the PoE cables heat up during operation but cool when power's off. The BER testing is statistically demanding. To achieving 99% confidence for a target BER of 10 to the minus 12, we need to transmit over 4 trillion bits. Yes, 4 trillion. At 1 gigabit per second, that takes roughly 77 minutes. At 10 gigabit per second, it's about 8 minutes. Our tester flags any frame with even single bit error, and each frame packs 1024 bits. So we get very fine resolution, catching even small changes as cables age. Tougher, but real. So what did we test? 6 cable total, all 4 pair PoE cables using 22 gauge copper, covering Cat6A, Cat6, and Cat5E constructions. The key differences are in jackets and constructions. Cable 1 and cable 2, both Cat6A, having an FEP cross filler and aluminum tape showing over the pairs, and thicker FEP insulation. Cable 1 use PVDF jacket, high temperature material, while the cables 2 through 6 using PVC jackets. Cable 4, it's interesting, using PVC cross filler instead of FEP. And overall, this mix gave us a clear view of how insulation, shielding, special jacket materials influence PoE performance under heat. All right, here are the BER results at different temperatures. Let me walk you through this table. At room temperature, all cables show the 0 errors. Everything works fine. At 90 degrees Celsius, still zeros for most of cables. But the Cat6 item 4 starts showing the link problems, marked as unsafe for not connected. At the high temperatures, same pattern holds. The Cat6A cables, both 1 and 2, perform the best. 0 errors across all the way up to 10 gigabit per second, even at 136 degrees Celsius. The Cat6 item 3 and both Cat5E cables also hold 0 errors up to 5 gigabit per second. But the Cat6 item 4 cannot maintain connection at high temperatures, total linker failure. Now, let's understand why the heat changed the performance. These slides show the insertion loss curves at 3 temperatures, from room temp to 136 degrees Celsius. As temperature goes up, the copper resistivity jumps roughly 44% in this range. That's pure physicals. We expect that. But look at the different rates of increase. The Cat6A item 2 stays below the limits at all temperatures. Why? Thanks to the thicker FEP insulation and FEP cross filler. Good design pays off here. Cat6 item 4 shows a much steeper increase as compared to item 5, even with similar FEP insulation, likely due to impedance mismatch. So the dielectric loss becomes more significant at high temperature and frequency, amplifying the thermal impacts on the cable performance. Semiconductor, different insulation design and materials, very different results. These slides combines insertion loss and crosstalk as temperature increases, give you a full picture of electrical performance changes. On the left, the insertion loss margin for cable Cat6A both dropped gradually but stayed above the limits. Again, thanks to their thicker insulation and larger pale spacing, so they can handle the heat pretty well. On the right is the worst case near and crosstalk margins. Here's something interesting. They actually improve as temperature goes up. Why? Because the jacket softens, loosens the pairs, increase the pair spacing slightly, and then reducing crosstalk. Of course, this is just temporary. Later, when the jacks get hardened and shrunk, you will get opposite results. We will talk about this later a little bit. Meanwhile, the item 4 shows a sharp increase in insertion loss or a sharp decrease in margins, eventually failing entirely, likely due to the poor thermal design. So the material stability, insulation thickness, pale spacing are critical for thermal performance. Now, the situation gets tougher with 136 degrees Celsius. Well, the aging is much more aggressive. Let me explain this table. We test the cables at temperature and after cooling to room temperature. Both items 3 and 5 start showing the errors after a few days. By day 7, the item 3 has 17 errors at 5G speed. The item 5 has 16. That's clearly evidence for singular degradation from prolonged heating. The item 4 never connects at all, total failure. But here's critical finding. After aging, we cool them back to room temperature and test it again. Results, 0 errors across all cables. What does this mean? The BR failures are thermally driven, not from permanent materials damage, at least not here yet. Now, let's take a close look at item 3 as example. This slide shows the near-end crosstalk and near-end ACR curves before and during and after thermal aging. When we zoom in on those worst-case regions, here's what we see. After 4 days, the curves start shifting. The crosstalk actually goes up, but the ACR drops because the insertion loss gets worse. After 10 days, even big shifts. This time, crosstalk gets worse quite a bit, and ACR keeps dropping because of it. Now, cool back to room temperature, some performance recovers, like ACR increase, because insertion loss goes down and carbon resistivity drops with cooling. But the crosstalk stays even higher than before aging. This tells us some thermal effects are reversible, but others are permanent. The reversible part, the thermal effects on carbon resistivity. The permanent part, the cable materials change with deformation, weight loss, and the cable won't go back to its original shape. Since all cables use FEP insulation, the jacket change drive what we say, except the PVC cross filler in item 4. Look at the weight loss plot on the left. Some PVC jackets degrade much faster, like item 4. There are big differences in thermal stability. The PVDF jacket on item 1, almost no weight loss, super stable. On the right, the graphic shows the physical changes upon heating. The jacket softens, expands when heat, hardens when prolonged heating, and then shrink when cooled. The bottom photos, after aging, some PVC jackets show a severe deformation and strong discoloration. But item 1 with PVDF jacket looks almost untouched. Here's what we learned. The jacket behavior is the key warning sign. The weight loss, hardening, shrinking, all leads to performance degradation. And beyond dielectric effects, these mechanical distortions change the pair geometry inside the cable, hurting the signal integrity. For long-term performance, the material selection is not optional. Okay, so let me wrap it up. 3 key takeaways today for you. Takeaway number 1, mechanical changes in the jackets due to their weight loss, shrink, hardening, compressing, serve as strong indicators of upcoming bit error rate issues. So monitor them closely. Takeaway number 2, design margins matter. Robust shielding, good cross filler, stable jacket materials, this boosts both electrical and thermal tolerance. Takeaway number 3, accelerated aging tests are essential. Don't just test the room temperature, but combine the safety, electrical, and mechanical tests to reveal long-term performance that standard testing misses. And one more thing, as PoE power levels keep climbing to 200 watts, these thermal effects will be only getting worse. It's time to design for thermal resilience? Yes, it's now. Definitely not after failures hit the field, right? Our next step is to evaluate the cable length effect. Present that at IWCS later this year. Before closing, I'd like to name our key contributors. The first, my co-author, Dr. Solomon Gurmer, and then our team, including Chris, Frank, Martina, Rodley, thank them all. If you have questions later, feel free to reach out. Our contact info is here. And now I'm handing to David for Q&A. I will be happy to take your questions. Thank you all.
Thank you so much, Bo. Obviously, extremely important information, especially with the convergence of powering and data that we're experiencing now over this same network infrastructure. And I guess that leads to the first question. With today's higher PoE systems, higher powered systems heading towards 200 watts, like you were saying, how would this change the way we think about cable designs? And should there be, in addition to the materials component, but what about the actual cable design itself?
Yeah, that's a good question. As this PoE power heading to 200 watts, you think about more power comes more current, and more current can generate more heat. That heat will be really hurts the cable itself during the operation. Like say the temperature can get pretty hard. From design perspective, uh, we're gonna have to have the design with much higher margins, which can offset those cable or degradation. And also we have to control the impedance to maintain the cable having good shape and protect the any compressing or shrinking on the cable core and change the original design. In that case, cable can maintain reliable performance over years of these high power operations.
Yeah. And, as we've been talking to users and contractors and others about the perils of counterfeit cabling, um, and not only the effects on fire safety, like you indicated, some of these materials, with smoke suppressions and flame retardants and other attributes, help to allow these cables to pass the plenum cable test. Counterfeit cables tend to use much inferior materials. And so is there a way that we can predict, and encourage folks to understand the impacts on data performance if they're using just basic olefins or basic materials in these counterfeit cables?
So let's say, like what I said, if for the high power application, the heat generated by the cable will be eventually hurts the material chemically and physically. So let's say chemically, the material is gonna degrade. I have no doubt eventually they're gonna lose something or they're gonna lose some chemicals or properties. And those things will be change the fault behavior. So the fault behavior, like the cable will be easy to burn because they lose the mechanical properties. And also, you might think uh, maybe losing some materials helping the foul behavior, like what I said, improve shorter frame spray and that smoke. But that's not really the case. Sometimes really materials dependent. And some materials behavior quite differently, like some details in our paper 2023 uh, uh, discuss about that part. And they can change the behavior dramatically in terms how the materials responds to the heat.
Right. And I guess as a follow-up to that, um,
Mhm.
what about the impacts on the non-plenum application or cable designs or applications like riser or tray cable or other halogen-free type solutions? What's going to be the impact on heat on those types of cables in the future?
Well, it's really depends. Well, you're gonna apply the cables, and for riser, you look like you apply it outside, maybe exposed to the sunlight or the water, like I said. Um, those things will really attack actually the cable from the jacket, starting from jacket. And well, when the jacket material starting, will the behavior losing the weight and contracted the cable core or something, they're really starting to change the fail performance of the cable. And in this case, we might not really think about the heat related to the issues in the riser or outdoor application, something like that.
Okay. Do you anticipate that UL requirements or other, standards, performance requirements for PoE cables, could be actually uh, generate exposures up to 100 degrees C, 130, 140, 150 degrees C that might end up requiring higher performance materials like fluoropolymers in these cables?
I'm not really sure about what you are gonna do, but from my perspective, we do need to recall about this the heat aging performance on the PoE cables, especially most of the PoE cables would using the indoor and with large bundles. And UR has some the task to take off the this heat inside of the cable, like in my slides showed. And I'm pretty sure our research or studies gonna attract attention for the community to think about how we're gonna address those thermal aging and the heat rise in the PoE cable application, especially for the high power applications.
Right. And of course, the ever increasing data rates for everything, AI, whatever. Will this impact the useful life of some of these cables and perhaps even reduce it? I mean, obviously, we've seen incredible data generations from the last 20 years, and so the warranties and useful life is going to be impacted.
Yeah, exactly. Normally we expect the lifetime 20 years. That what I said in the slides. And as our data shows, actually, 20 years at a certain temperature is unapproachable. And also, it really depends on what kind of materials you can use, right? For some materials, maybe perform even uh, over 50 years at even higher temperatures, like 150 degree. But for some materials, they just starting the degradation, maybe starting from the first day on site.
Yeah. This may be a little detailed, but in your PVC jacket 4 that you talked about, and the fact that it may have decomposed at a faster rate, is that formulation dependent? And what can you infer from the different decomposition rates?
Yeah, that's really good question. First of all, I would like to say I don't know the formulation on these jackets, and
Hmm.
sorry I couldn't go detail on how they formulated. But in terms of our results, the item for jackets actually performed really bad compared to other jackets, PVC jackets. And the one slide we show the weight loss plot, the item 4 actually stands out for fasting weight loss over time at 136 degrees C. And those actually, the jackets on item 4 degraded really fast and was really bad. And also the item 4 has the same compounds for PVC cross filter. So that will be bring other fact into the observation we had. So is that answer your question?
Yes. No, it obviously, formulations make a difference for sure. Um, so they need to be tested. Each cable needs to be tested for long-term
Exactly.
aging. Um,
Exactly. And also we introduced some the method to test it. So hopefully the community will have or develop or some method to further testing the thermal or thermal degradation properties on these PVC compounds.
just two or three more questions here. What is the highest temperature rise that you may have seen on a bundle of cable?
Yeah, that's a really good question. In my introduction background slides, we say in terms our early study from Thibault's study in 2027, and he published that results in at IWCS and using a bundle with 100 cables. The center of the bundles can reach up to uh, like a 180 front height. So which means, in other words, the temperature increase can be around 90 degree something degree Celsius. And but as I said, some study even shown in the worst case, the center of the cable can reach up to nearly 200 degrees Celsius. So basically, not much material, polymer materials can withstand that temperature.
Um, we talked about plenum versus non-plenum cable materials and designs. Um, uh, but particularly in European applications, the CPR, uh, construction product regulation applications, do you think that there's going to be some added performance requirements, perhaps beyond safety, but performance requirements uh, that obviously these heat generations for halogen-free solutions are going to affect?
Yeah, that's a good question. Actually, for as a materials engineer, I would be a little bit concerned about these low smoke hydrogen free compounds for the high power PoE applications. So let's say typically they use ATH for the thermal retardancy. So ATH has the composition temperature below 200 or 180 or 190 degrees Celsius. So for those high power PoE applications, especially big bundles, the temperature will rise in the center will be really hurts the these low smoke hydrogen jackets, obviously. But in that case, DMH will be a different story because its decomposition temperature will much higher, over to much higher than 200 degrees Celsius. So in that case, so that kind of a thermal retardance will be help stabilize the jackets and these high power PoE applications.
Yeah.
So it really depends on what kind of jacket materials you're gonna use.
Yeah. And one last question. What should cable designers prioritize if they want to improve the thermal resistance? Is it materials, shielding, pair geometry, or something else?
Yeah, that's basically what about exactly what our research about. We're trying to clarify which pattern or which one we're gonna go first, which one is our top priority in terms the high power PoE applications. As I said, the materials will be the top priority to addressing these thermal aging challenges. And the stable material and the long-term performance duration will really help the thermal resilience under this heat stress during the PoE operations. And the second thing is the design, like the pile geometry and installation thickness. The work comes to play. Just one moment. So those will help stabilize the electrical performance during the cable age. And the final one would be the the other thing like I want to think about the other factors. I would like to say the cable designer need to have good control of the impedance so they can maintain a good electrical performance under this heat stress.
Very good. Well, listen, thank you, Bo. Very much appreciated, and some great questions. Again, a very interesting and important topic on how we're going to address future designs, and many of these cables are going to generate more heat and more issues. So thank you very much. I do want to remind you that Bo can be reached at the email address shown on your screen. I know Bo had provided some other contact information previously as well. And also, this presentation has been recorded and will be on accessible from our website and on our YouTube channel at IWCS.org. And I'm sure you'll want to listen to this again and understand it more fully, and also share it with your colleagues. Normally it takes about a week or so to have it uploaded, so be on the lookout for that. Our next webinar event will be a technical paper on Friday, April 17th. Typically, it's the third Friday of every month, and it'll be at 10:30 a.m. Eastern USA time. So we hope you will look out for those announcements, and feel free to share them with your colleagues so they can join in and listen to these excellent presentations. I also want to remind you again, with just like Bo and so many others who have contributed incredible technology information, I hope you are considering submitting your own research and perspectives to promote the work that you and your company are doing, and that you'll be submitting a technical paper. I saw Bo is planning on submitting a follow-up paper, so thank you for that. But it's very, very simple. The call for papers from our website, a very simple one-page description of your research and conclusions would be helpful for us to review it and accept it and include it in our conference coming up this November in Orlando. So please consider that. The deadlines is rapidly approaching, Friday, April 10th. So please consider submitting your own technology and your own papers to help expand and the growth of our industry globally. Also, I want to make sure that we thank our partner level sponsors who not only provide technical content to our conference, but their strong leadership and generosity also enables us to bring these important innovations and information to you and our global community. So again, we thank these leading suppliers in our industry for their support. And again, as I mentioned, over 74 years we have been putting on this conference, and we're excited to be looking forward to our 75th anniversary conference. We're going to have a fun celebration, some fun entertainment on the first evening, but more importantly, we also will be having our exhibition with leading suppliers, and also the presentations of many important technical papers and trend topics. So please make plans to attend and join us November 1st through the 4th at the Gaylord Palms Resort in Orlando, Florida. And a really fun place to go and stay, and bring your family. It will be exciting, not only our own celebration event, but also clearly you've got Disney and Universal and all those fun things. A lot of new stuff has happened over the last several years. So bring your family, and we would enjoy being with you in November. So with that, thank you for attending today. I hope spring has come to your neck of the woods. It looks like it might happen this weekend here in the USA. So have a great weekend, and a happy Easter that's coming up next week, I understand. And take care of yourselves. Look forward to being with you again next month.
Thank you,
Thank you,
Dave.
Bo.
All right, see you later.